Hey, Natasha.
Hi.
What would you like to work on tonight?
Um, I suppose I have a practice test for a chapter I'm doing in class.
Okay. Yeah, the practice would be good. I can work through it. I can give you problems like those, combination. Yeah, if you want to send it over, that would be extremely helpful.
Okay. That should have sent.
What chapter are we looking at now? Is it like
It's
7?
chapter 8.
Chapter 8. Okay.
Mhm.
All right, there it is. I see that you sent over something for us to look at. Okay, so bunch of questions here. Lots here. All right, I'm just looking this over. We actually did the last question in a previous dialogue, I think, but I'll just start at the beginning, and you can let me know if you want more examples like ones or the others. We'll just go through some problems here. Let me share my screen and we'll get started.
Okay.
All right, so if you're seeing my screen, first question says, here's the function y equals 1 over x minus 1. Do you have any idea what that looks like without seeing a graph of it?
It's generally, I don't know how to describe it in words.
Okay, fair enough. There is a vertical asymptote at 1, which doesn't really matter because we care about from 3 to 4. So it looks something like this, and that's your rough sketch. Okay, so we're taking the region from 3 to 4, and this is what we're revolving around the x-axis. Remember I said that you always want to indicate which axis you're going around.
Mhm.
And that's important here. So is this a disk or a washer problem? Sometimes washer problems are called ring problems. Do you know the difference?
Not really.
Okay, so the disk problems have no gap or no space between the line or the axis that you're revolving around. Do you see how this region perfectly touches the axis there? There's no gap.
Mhm.
And that is a disk problem. Okay. So the disk problem, the general formula, and do you get a formula sheet on your exam?
I do not.
You do not. So it's pi r squared dx, but r is really a function of x. In this case, it's almost always your y. So that's what so we're substituting in for r this 1 over x minus 1 squared. Okay.
Okay.
And then the pi I'll bring to the outside, and then your limits of integration are whatever the limits are along here, which is from 3 to 4, and then dx. Okay, is there anything is how would you integrate this, I guess, or like what do you see when you look at this problem here? Any idea how to proceed?
Well, not 100% sure.
Okay, I'm gonna just square the top and the bottom like this, and we still have this pi on the outside, 3 to 4, and dx. And I think chapter 7, based on what I saw last time in chapter 6, in chapter 7 you learned that the integral of 1 over u du is the natural log of the absolute value of u plus c. You remember that from last chapter? So if we can make this look like that, we're in good shape. So u in this case is x minus 1, and then du is dx. You take the derivative of both sides. This is a u sub integral. All right, so the way this works is you substitute in your u, and instead of dx, you put du, and then you have a choice. You can either change the limits of integration, or you can put the old ones back in. Do you, which do you prefer? Do you like to change the limits of integration? Are you not sure? There's a lot of ways you can do this.
Sorry, my mom just came back in my room.
So I'm going to just suggest we change the limits of integration. So you do that by putting the lower bound in for x. So it's 3 minus 1 is 2. So the lower bound becomes 2. The upper bound, you take that upper number 4, which is 4 minus 1, 3. So from 2 to 3. Right. And then you just integrate this thing. So the power rule, this becomes minus 1 over u pi, and then you evaluate from 2 to 3. So that's pi negative 1/3 minus negative 1/2, like that. You just put the bounds in. And so this becomes pi minus 1/3 plus 1/2. So that's like minus 2/6 plus 3/6. So this becomes just pi over 6 as your final answer.
Okay.
What about this problem is difficult or unclear, or where you wouldn't know if you could do it on your own? We started by making a sketch, which you may or may not have to do. We then chose which type of volume we're going to make. And then, oh, you know what? I'm sorry. I did a volume. This was actually just asking for the area, but it's the same principle of this. So for the next one, we will definitely do the area of it. Sorry about that. It's been slightly easier. Because he said chapter 8, and I remember us doing volumes in chapter 8. Okay, let's look at letter B. But again, if there's anything that's unclear, like please tell me so that I can do better. I can explain better or give more examples to help your understanding. Okay, so this time just the area. Just the area. Okay, and they want the area from 1 to 2. Do you remember generally what a cubic looks like?
Yeah, it's like a squiggly.
Squiggly thing. I
It's the
like
best
that.
way to describe.
I like that. Yeah, that's that. This one is moved up to and stretched, so it would look something more like this, like that. And we're just going from 1 to 2. So we're getting that region there. So the area is just the integral from the lower limit to the upper limit 4x cubed plus 2 dx. So if you would be so kind, would you mind finding the antiderivative, evaluating at the 2 endpoints, and letting me know what you come up with for this one?
I got 17.
That is correct. Okay, that means that you've got a good idea of how to do the antiderivative stuff. The next problem C, it doesn't have enough information, I guess, just at first glance. They want the area between the curves.
Mhm.
And this is, I mean, to me, this is more of your test question because you got to find the area between the two curves. That means you got to find where they intersect. You have to set them equal to each other. And in this case, you move the x over. It's x squared minus x equals 0. Factor out an x. So x equals 0 and x equals 1.
Okay.
And when there's only two bounds like that, those become the limits of your integral. So the area between curves is top minus bottom. And sometimes you don't know which is the top and which is the bottom. So let's just say you think, well, it's x squared minus x. Like you don't do anything more than that. You're just like, all right, I got it. You get 1/3 x cubed minus 1/2 x squared. Evaluate from 0 to 1, you get 1/3 minus 1/2, and the other endpoints are 0. And this ends up being negative 1/6. Okay, and this is wrong. It's not completely wrong, but it is wrong because we had the order incorrect up here.
Mhm.
Okay, so if you get a negative answer, there are a couple possibilities. One is that you did it in the wrong order. Another is a mistake made somewhere along the way. There's a couple other possibilities, like not getting all the intersection points, but it's not a good idea to just change your answer. You really want to figure out which is the top and which is the bottom. So to do that, you pick a point like x equals 1/2 because it's between 0 and 1, and you test it in here. So 1/2 squared is 1/4, and 1/2 is just 1/2. So whichever one is larger, that one is on top. And that means you should switch the order of integration on that.
Mhm.
Okay. So if you understood that, so like this should have been x minus x squared, and then you'd flip all this other stuff along the way. You would actually get positive 1/6. Okay. So new question for you. Let's say it's y equals square root of x and y equals x. Okay. And we want to go from 0 to 1. Could you try this one on your own, please? And correctly figuring out which one's on top and which one's on the bottom.
Okay. Is the y equals square root of x on top?
How are you doing on this one?
Is it y squared of x on top?
I'm sorry, say that again.
Y square root of x is on top.
Yes, so the square root actually gets taller before x does. Yes, it becomes this little window there. because like the square root of 1/2 is bigger than 1/2.
Mhm.
Does that sound? No, that doesn't sound right. Why am I? I'm gonna have to graph this myself because I'm really struggling with this. Yeah, I'm sorry. Yeah, this is right. Yes, this is a correct picture. So you have a final answer for this?
Not yet.
Okay.
Oh.
I'm gonna just start working out the solution here in case you want to look at that later also. Okay, so that's 2/3 minus 1/2, and then just make a common denominator on that. So we should get just 1/6 for this.
That's what I got.
Great. All right, so there's a number of questions in this practice exam that say calculator okay, and I'm sorry if I've asked, but are you actually allowed to use your calculator on this exam?
When I take the actual exam, no.
All right, so let's skip those. They're designed to be done with a calculator, and it could be problematic if we do too many like that. A lot of times you do need a calculator to actually do these problems because they don't work out very nicely. Okay, what is the volume of the solid generated? So this time it actually does want a volume. And they give you all the information you need here. Like you don't have to do any work. You don't have to figure out intersections. You don't have to figure out top and bottom. They just want you to figure out the volume with this information. But if we did make a sketch, do you recall what a secant graph looks like?
Is secant the one that just looks like a bunch of cubic functions repeated over and over again?
That's a tangent or a cotangent. Secant is the reciprocal of cosine. From where cosine starts
Oh yeah.
high, and it goes low, and then it comes back. And so these places where it crosses ends up being these vertical asymptotes. And then what it is the U part where it touches. I'm just going to grab another color here. It's like this. So we only want it from 0 to x equals 0 to x equals pi over 3. So I'm going to do a better job of showing you what this looks like. X equals pi over 3. Try and snip this in so you can see the region we're talking about here. Do you remember if your instructor was big on like actually sketching this?
Not really.
Not really. So it's all of this region here. Okay, so your volume though, it depends on whether it's a disk or a washer. And this one is a disk again, because there's no gap between the line that you're revolving this around. Actually, I assume it is revolved around the x-axis. Yeah, it is. So there's no gap. So this is a disk. And a disk has the formula a to b pi r of x squared dx. So it's your function, which is generally y. In this case, it's pi secant squared x dx from 0 to pi over 3. Do you recall the antiderivative of secant squared?
Tangent.
Or tangent, yeah. Perfect. So this is pi times tangent of x evaluated from 0 to pi over 3. So this becomes pi parentheses tangent pi over 3 minus tangent of 0.
Okay.
So we do need to evaluate that. Tangent pi over 3 is sine pi over 3 or cosine pi over 3. It's the same at 0, but that's kind of a nice one. It is 0. So sine pi over 3 on your unit circle, there's kind of those 3 places you need to know. There's 30 degrees, 45, and 60. But when you get through trigonometry, you realize, oh, it's pi over 6, pi over 4, and pi over 3. There's all this, mixing or switching of things. Right here ends up being 1/2 comma square root of 3 over 2 is the ordered pair. Sine is the y value over the x value, so square root of 3 over 2 over 1/2.
Mm-hmm.
So that ends up being just the square root of 3 times pi.
Okay.
All right. Let me go look for another problem here. Okay, so I should have you try one here. Let me have you find the volume of the solid y equals, let's go x square root of x from 0 to 4. Okay, and you're going around the x-axis, and this is a disk problem. And then we'll do some washer problems after this, but probably good to have you try one of these before moving on to something new.
Is it 16?
Well, did you use the formula with the pi in it?
I forgot to write the pi at the end.
Okay, so yeah, you're squaring this. So let me give you the full information. 0 to 4 square root of x squared. So it becomes just x. And then you find the antiderivative, 1/2 x squared, evaluated from 0 to 4 pi. So I get it's 1/2 4 squared times pi. I get 8 pi.
Wow, I just forgot to write things down. I can't write. I wrote it at the beginning and then I did not write it at the end.
I have a really good suspicion that you're a really good student. And I know you said math is not your, like, you don't enjoy it, but there's nothing here you can't do from what I can infer from our interactions. Like, you are totally capable of doing this. And sometimes you just gotta, and this is me just giving a little bit of like life advice, and I will not do any more in this. Like, whatever you do in your other classes to do really well, if you can apply those principles here, you will get so much better at this. And then it's over. Then you don't have to do it ever again. And that's all I'll say on that. So let's look at number 6 together. We have not done a washer problem. This one appears to be a washer problem. All right. So I'm going to make just a couple of changes though, because I want to do it in around the x-axis first to make this more pleasant, we'll say. So the first thing is we're going to graph this region. So you know that x squared looks like this right here, and y equals 4 looks like that. So the first thing I would do is set them equal to each other. And you already know the answer to this. You know that x equals plus or minus 2. But I imagine I've also said that we're only in the first quadrant. So this is the region that you're revolving around the x-axis.
Mm-hmm.
Now this is different than the previous problems because there's now a gap. This is a gap. See how there's a distance between the thing you're revolving around in your area. So when there's a gap like this is what is called a washer problem. Okay, so I'm going to just recopy this down here and remove these terms. Okay, so the washer problem has a slightly different formula. Okay, so the washer problem, let me get back to this. The area is pi integral from a to b again, big R squared minus little r squared dx. And the big R and the little r are what you have to figure out. So for this problem right here, I'm gonna try and show you big R in blue And big R is always the distance. It's always from the whatever you're revolving it around to the top function, because it's always top minus bottom. The green R, I'm gonna use green for the little r, it's changing. Like over here, it's really small, but on the right here, it gets really big, but it always corresponds to the bottom. So big R in this case, it's always 4. Little r though changes. Little r is x squared.
Okay.
Okay, and sometimes it's good to check like the endpoint, like when x is 0, little r is 0. In the middle, like when x is 1, little r is 1. I don't have this drawn to scale. And when x is 2, little r is 4. So it does work. Like it does actually capture the big R and little r. So to do this now, we have to find the bounds, the limits of integration. It is not 0 to 4, it's on the x. So we need to figure out this intersection point. It is 2, 4. So you're integrating from 0 to 2. Because you're doing an x-axis integral, these numbers come from your x-axis. Your big R is 4, your little r is x squared. It's good to write it out and not try to simplify it as you go. Now you can simplify, and then you take your antiderivatives. That's 16x minus 1/5 x to the 5th times pi, and you're going to evaluate from 0 to 2. Now I keep giving you nice like lower limits where it's 0. I mean, you should expect on a test to not always make this nice, but that's to kind of like speed up these calculations. Otherwise, we'd never get through them. So it's 16 times 2 minus 1/5 times 2 to the 5th times pi, and then minus 0. So 32 minus 32 over 5. And then you got to make a common denominator here. And if you don't have a calculator, you got to multiply by 5. So this becomes 160 over 5 minus 32 over 5. Don't forget to bring down the pi. And you get a lot of answers that start looking like this, like 128 over 5 times pi. That's what it is.
Okay.
Is there any steps here you would like me to discuss again or clarify or go over again?
No, I think I'm good.
All right, so the next problem I want us to do is I want to do a volume, and it's between y equals x. It's the area between, we've already done this, and y equals square root of x from 0 to 1. So this is the blown up view of what this looks like. Square root of x looks like this, and y equals x looks like that. And we're going to go around the x-axis again. Okay. So this is a washer problem. It's a washer problem because from 0 to 1, there's a gap between this region and the axis we're revolving around. And if we were going around the y-axis, we would have a similar problem. We would have the same gap. Okay. So you got to figure out your big R and your little r. Okay. And what I used to do, and I do find this pretty useful, is to actually draw out like a potential big R. That way I knew which one it is. In this case, big R is the square root of x. And then little r, now that we've got some technology, I can do it in another color. And I'm only offsetting them so that you can see that they're different colors in different places, but it's at the same place is where you're doing it, and that's x. So again, our formula is pi integral a to b big R squared minus little r squared dx. So this equals pi integral 0 to 1 square root of x squared minus x squared dx. So would you attempt to find the antiderivative and evaluate it at the limits there and see what you come up with for a final answer?
Okay. I got 1/6 pi.
Yeah, you keep getting that number over and over again, right? That's a common one that you might see. All right, so let's go back and do the actual problem that it said to do, because it is a y-axis integral. Did you get any feel in class if this was going to be something you were going to see? Y-axis, meaning like did the instructor say, yeah, we're going to have this on the test, or no, it's not? Any idea on that?
I'd be willing to bet it's probably going to be on the test somewhere.
Okay. So the AP does not cover this. And I mean, it's kind of interesting that you have to even deal with this, but you know, that is the case. So y equals x squared looks like this. And then x equals 2 looks like this. And the x-axis here. So it's, and I guess I'll do this in a different color this time. I'll show the shaded area in green. And this time we're revolving around the y-axis. Okay, so this is a washer problem because there is a gap between the region you care about and the axis. So when there's a gap, it's the washer method. And the difference between y-axis and x-axis is that now you think in terms of, sorry, got the right wording, wrong wording, right minus left.
Mhm.
Okay, and the other variation is that you need to solve for x. So in this, so like up here, you have to solve this for x equals square root of y. Sometimes they already solve it for x, and then it's great. Sometimes they don't. So like instead of thinking of this thing right here that's written, instead of thinking it as y equals x squared, you want to think of it as x equals square root of y. And I know as a student, I remember feeling like, God, that's really confusing. That's just the way these are. So the y-axis are a little bit more difficult to do that. It's still a big R minus little r problem, but now you're integrating with respect to y. So some books like change this to C to D, but it's really A to B. It's A to wherever this is, B up here. And the intersection point is again 2, 4. So you end up integrating, there's a pi. You end up integrating from 0 to 4. Your big R is the right. So that is, let me grab a different color. That's always this right here. It's always the 2. It's always a distance of 2. And then your little r is the one that's changing. It's the one that we just mentioned here. It's the square root of y squared.
Okay.
And there's a pi here. So would you give this a try integrating from here and letting me know your final answer?
Okay. I got 8 pi.
8 pi. Let me double check here. So this is 4 minus y. So your antiderivative is 4y minus 1/2 y squared, evaluated from 0 to 4 times pi. So that becomes 16 minus 8 times pi, and it is in fact 8 pi. Excellent. Fantastic. Okay, let me look here, see what else we can do. Did you get any arc length problems in your homeworks that you remember? If you know idea what I'm talking about, that's okay too.
Not that I remember.
All right, let me, so the formula here, this, you've got to have this formula to be able to do it. I'm going to just double check because I don't want to give it to you wrong, but it's in your book. Some instructors actually spend the time like deriving this for you, and you're like, I don't care. Just don't. So this is the formula. It's 1 plus y prime squared inside your dx. So you're always given a y. So step 1 here is to calculate y prime. So when you take the derivative of this, if you remember derivatives, sometimes you go back and forth, you got to remember power rule, you bring that down. It's 2/3, bring down the exponent of 3/2, x to the 1/2 power. So it just reduces to x to the 1/2, okay? And y prime, you then square it. So you actually have to square this number here. So it becomes x to the 1/2 squared, which is x. Okay, and the reason you do all that is because to find the arc length, or length of the arc, I don't know, I call it arc length. Maybe there's a English thing there that I don't understand, but arc length is what I'm used to seeing. So this becomes the integral from 0 to 3, those bounds are given, square root 1 plus x dx, because y prime squared we just calculated right here.
Mhm.
So when you look at this integral, and if you haven't done any in a while, sometimes you're like, how do you even do this? Well, this is actually a U-substitution integral if you want to do it like totally properly. Your u is 1 plus x. Your du is dx. So the length of your integral is u to the 1/2 power. Instead of dx, you put in a du. And like we did in an earlier problem, you do want to change the bounds here. So you plug 0 in for x, and then you plug 3 in for x. And that changes your bounds from 1 to 4. And the reason you do this is you're going to do the integral with respect to u. So you might as well change the bounds so that you don't have to back substitute and put the old bounds back in. In some cases, you're really saving a lot of time here.
Mhm.
All right. So would you be so kind as to find the antiderivative of this and let me know what you come up with for this one? I'm going to just start working this out. So if you want to look, you can, but just letting you know. One to any power is always one. So the right side often, or the other one is usually just reduces down. And then
Mhm.
4 you can turn into a 2 squared. And your exponent rules, if you remember, they just multiply. So you end up getting 2 times 3 halves, which is just 3. So this ends up being 2 to the 3 times 2/3. 2 cubed is 8. 16/3 minus 2/3 equals 14/3. And I think there's a nope, this was arc length. So this is it. This is your final answer. Last comment I'll make is that most of the answers today were kind of unfriendly. It's hard to make these nice, so you may feel good if you know you're getting a lot of these unfriendly answers on your exam.
Okay.
All right. Well, you did great. You did like 3 days in a row of math, I think, with me. So I really appreciate you scheduling, and I hope you do really great on your exam. If you have time, definitely try to work through some of these problems again. And I'll send you the notes and the screen recording here shortly.
Thank you.
Have a great night. Bye now.
You too.